Now, in every single one of the volume examples that we've looked at so far, we have a solid that's resulting from a revolution around an axis, which means that cross-sections will be circular in nature. But they don't always have to be circular in nature. We can build solids a lot of different ways. Our cross-sections don't have to be circles. They could be triangles, they could be squares, they could be rectangles, they could be trapezoids, they could be irregularly shaped, like that loaf of bread that we talked about. There are lots and lots and lots of different possibilities here. So how do we deal with the less regular ones like those circles? Well, remember that we're just taking infinitely thin cross sections of our solid, finding the area of each cross section, and adding up the volumes of each one of those based on the infinitely thin thickness. We're going to use those integrals, right? So this is the concept that we saw at the very beginning of this unit, where we talked about finding the area of a cross section and integrating from A to B. Remember that dx gives us our thickness, the area of our cross-section gives us the other two dimensions, and we multiply two dimensions times one dimension, we get that volume, and then we add them all up. And it would be a dx problem if we're slicing perpendicular to the x-axis. It would be a dy problem, and our area would be a function of y instead of a function of x if we are slicing perpendicular to the y-axis. But either way, we're just adding up a whole bunch of different areas. So the trick is, can we come up with this function, this area function, as a function of x or possibly y? So that's the goal here. So in example 10, we're going to use the same bounded region, and we're just going to change the shape of the cross section. So we've got the line y equals x plus 1. Which is a line of slope 1 going through the y-axis at 1. And we've got y equals x squared minus 1, which is a parabola whose vertex is at 0, negative 1. And the region bounded by those two shapes is going to form the base of a solid. Now, for each one of these solids that we're generating using that base, we're going to stick with cross sections perpendicular to the x-axis. We could do perpendicular to the y-axis, but remember that if we do right minus left, it's going to be parabola minus parabola for part of it, and then parabola minus line for another part of it. And we could definitely do that, but it would require using two different integrals to set it up. We'd have to solve our parabola for y and get x equals something in terms of y with a plus or minus. But to keep things simple, we're just going to stick with each one of these shapes being having cross sections of a particular shape when we slice them perpendicular to the x-axis. So that means that this little thickness right here is going to be dx, and this is going to be our side length. We'll call it s. S is going to be a function of x, is going to change depending on what x is, and to find the height of this, it's going to be the same as it always is, right? We're going to find the larger value and subtract the smaller value, the top endpoint minus the bottom endpoint. The top endpoint is from the line, so that's going to be x plus 1, and the bottom endpoint is going to be from the curve, that's going to be x squared minus 1. So when we subtract, we're going to find that we've got x plus 2 minus x squared. And that's going to be the length of the side, and that side is going to depend on, the side length is going to depend on the value of x. And it would make sense at this point to maybe figure out what our endpoints are, right? So our points of intersection here, we'll have the point of intersection negative 1 comma 0, right? When x equals negative 1, y equals 0 in both of these equations. And then this one up here, that one might be a little bit harder to find, but we can set those equal to each other. X plus 1 equals x squared minus 1. And we can subtract over and get 0 equals x squared minus x minus 2. So x plus 1 and x minus 2. So that negative 1 that we already knew about came from that factor. And then we have x equals 2. 2 is the x value. The y value will be 2 plus 1, which is 3. Quick check. 2 squared minus 1 also gives us 3. So our x values are going from -1 to 2 for each one of these, because that's those points of intersection. So the only thing that's left to do is to come up with the area function, and the area function is going to be determined by that side length, right? So our side length and also the shape, right? So we're gonna have to know the area formulas for each of these shapes. So for example, we're gonna have squares in the first one. Our cross sections are going to be squares. So for example, if you imagine this is one side length of the square, and then we're going to come up off of the page. I can't make my mouse come off of the computer screen towards your face, but come up off of the screen and then come back over and then back down again to get a square. And then for each one of these x values, we're going to have a different sized square because s is going to change. So anyway, this is s of x, and since it's a square, this is also s of x. So the area as a function of x is equal to s of x squared. So we're going to integrate to find the volume here. We're going to integrate from -1 to 2. Of our area function, which is s squared. So this is going to be x plus 2 minus x squared, all squared. And then we have our thickness, right? Our thickness is dx. And I'm just going to set up, but do not solve for all of these. We're going to find that it's going to be an extremely similar integral for these guys. Okay. The next shape we're going to deal with is a rectangle. So this is one side of the rectangle, and we'll call that S, or S of x. And then the other side of the rectangle is going to be a constant of 2. Okay? So the area, in this case, the area function is going to be the area of this rectangle, which is base times height, or 2 times S of x. All right, so this integral will be a little bit easier. We'll go from -1 to 2. Of area, which is 2 times x plus 2 minus x squared. We don't square s in this case because our second dimension of our rectangle is, of our cross section I should say, is a constant of 2. Okay, so this is one dimension right here, this is a second dimension, and then this dx will be our third dimension. All right, this time our rectangle is going to be a base of s and a height of 5 times s. So our area is going to equal base times height, which is going to be 5 times our side length squared, right? 5 s of x times s of x is 5 times s of x squared. So when we integrate this, we'll integrate again from -1 to 2. We'll have a 5, and then we'll have our x plus 2 minus x squared will be squared this time, right? Because our height is not a constant, our height is changing as our base changes as well. Okay, so you'll notice that this integral right here is the same as our first integral with the square, except we've got a constant factor of 5. So this answer will be 5 times bigger than A. Answer from part A. All right, so really we're just turning each one of these into a regular two-dimensional area problem. So we're going to turn this one into a two-dimensional area problem. We've got ourselves a quarter circle. And we've got s of x right here, and that's a radius. So we're going to have s of x up here as well. So the area function is going to be 1/4 the area of a circle whose radius is s of x. So 1/4 pi r squared, where r is s of x. So 1/4 pi times s of x squared. So when we integrate that, again, we're going to go from -1 to 2, and that pi over 4, we could pull that out front, just like we could have pulled this 2 out front and this 5 out front. But since I'm not evaluating, I'm just setting up, I'm not really going to worry about it too much. But notice that we keep on using this same x plus 2 minus x squared each and every time, because that is the side length that we determined at the very beginning up here, right? So we're going to see this show up in every single one of these, regardless of the shape of the cross section. Okay, so semicircles, pay attention to semicircles. Those tend to be a little different because instead of having the radius be s of x, this time the diameter is s of x. So that's our diameter. But the area function is going to be 1/2 pi r squared, but don't replace r with s of x. Replace r with 1/2 s of x. And that's a very common mistake. People will forget to cut this in half. So that's going to equal 1/2 pi times 1/2 s of x squared. So we're going to square that 1/2 to get 1/4. That 1/4 gets multiplied by the 1/2 to get 1/8 times pi times s of x squared. Okay, so when we integrate this from -1 to 2, we'll have pi over 8 is our constant this time, and we'll take x plus 2 minus x squared squared, and there would be our setup, but do not solve. All right, and trucking right along here, we've got an isosceles right triangle. The base is one of the legs, short leg, long leg. There is no long leg, they're both short because the legs are equal in an isosceles right triangle. So this is s of x, so this is also s of x. So the area function is 1/2 base times height is 1/2 s of x squared. So the area for this one would be the integral from -1 to 2 of 1/2 times x plus 2 minus x squared squared dx. So you're noticing that with the exception of b, all of these are going to integrate the same trinomial squared, and then they only differ by some scalar constant, whether that constant is 1 or 5 or pi over 4 or pi over 8 or 1/2. That's going to be the only thing that changes on these problems. Two more, and again, we're just doing area problems. This is back to geometry. Isosceles right triangle again. This time the hypotenuse is the base. So we've got something like this where the right angle is here, and this is s of x. So if you remember your special right triangles, in order to find the legs, you have to divide by the square root of 2. So this is s of x divided by root 2, and this is s of x divided by root 2. So if we call this root 2, if we call this the base and this the height, like we did over here with the 2 legs, then the area function is 1/2 times s of x over root 2 squared. So 1/2 times 1/2 is 1/4, and then the s of x gets squared. So same idea as this one, but instead of a 1/2, we have a 1/4. So our setup but do not solve integral would be the integral from -1 to 2 of 1/4 x plus 2 minus x squared squared dx. Okay, and again, we're seeing that x plus 2 minus x squared squared show up in all but that second integral. And again, the reason that second integral didn't have the squared here is because one of our 2 dimensions was a constant. All right, last one, equilateral triangle. You may have a formula memorized from geometry or math team if you're into that stuff. If you don't have the formula for the area of an equilateral triangle memorized, it's not so hard to derive. If you know your special right triangles, I'm going to take that s of x and divide it into 2. S of x over, oops, not square root, just 2, and s of x over 2. This is a 30, 60, 90 right triangle, so the height is the short leg times the square root of 3, so root 3 over 2. So when we do 1/2 base times height, we take 1/2 the base times the height. The area function is the square root of 3 over 2 times s, nope, not times over 2, 2 times 2, which is 4, times s of x squared. So when we set up this integral, everything stays the same except that constant is now root 3 over 4. And everything else stays 100% exactly the same.